Okay, so from what you gleaned yesterday, you guys have your notes out from yesterday, so you could like help yourself answer some of these questions. Okay, so as we talked about me and you yesterday in the video, we talked about a periodic trend, and a trend is just like a pattern you see, right? So the trend in this class should be you should be saying about 25 to 30 minutes, right? You're going to do something. The trend is that if you do well and practice every day at homework, then you're going to do well on the test, in the labs, and the test. So, in the class. So the trends on the periodic table are actually more about properties, and all these properties are related to the electrons. So if you have electrons that are really free and able to move away from the nucleus and go react someplace, they're very, very, very reactive. If you have electrons that are really close to the nucleus and they're stable and they do not leave the atom, then that element is not as reactive. So it's all about where the electrons are in location around the nucleus that determines their reactivity, aka their properties. So we have to understand what the size of the atoms are and how likely it is for an electron to leave the atom. So the first trend, so everybody float your guns, you got them? Okay, got them? Yeah, both? We need both. Okay, right here too, right, okay, so we're using our fingers. I made this up when I was your age to figure out which way the trends went. Your fingers are arrows, okay? And do you know how to make a picture? Take your right hand, turn it upside down. Take your left hand and point it toward your head, like this. This is a picture. Yeah? Can you figure this out? Some of us are like, we don't know orientation. Okay, so your right hand is the atomic radius. The atomic radius is the only one that increases to the left on the periodic table and down the periodic table. So what is the largest atom? What's farthest away from the corner of your hand here? Francium, way down here is the largest atom, right? It's got the largest atomic radius. Right hand radius. Okay, that's the why that one goes this way. Everything else, electronegativity, ionization energy, and electron affinity increase, those trends increase up a group and across the periodic table to the right. So everything else increases this way. So on the test, I'm going to see you going, or you can just draw it like this. That's okay too. But this is the general trend. And this makes sense because if you think, and if you went through some of the worksheet, and if you listened to one of the Bozeman videos, and I'll show you in a second, if you think about a humongous atom, how far away is that outer that valence electron? How far away? Far, or a long distance away or a short distance away? Long distance away. That free electron, so if I am the nucleus and Kendall's my valence electron, he's over there in left field, right? He can go and react anything, right? So if I'm francium, the largest atom, and Kendall's my valence electron, that valence electron, the ionization energy of that electron is low because it takes no energy whatsoever to distract him and make him go off in left field, right? He's an electron. It doesn't take much energy to get him away from me because we're so far apart. The electronegativity and the electron affinity, they go together as well. Those are low numbers, but the atomic radius is huge. But if we're talking about like fluorine, which is going to be one of the smallest atoms, so let's say I'm fluorine's nucleus and you're my electron. Is it going to be hard to take her away from me? Incredibly hard. Because one, it's a small atom. I'm really close to my nucleus, but the electron's really close to me. The ionization energy is going to be like, 1,000 joules to me. A really, really high number because we're so attracted because our distance is really close to each other. So the farther away something is from the nucleus, the easier it is to plug off. Because that's what the ionization energy is really low. The closer something is to the nucleus, the harder it is to plug off because it's so magnetically, our opposites attract kind of deal here. And that's called Coulomb's law. Okay, so explain why the atomic radius trend increases down or across and down. That's going to be related to the ZEF, the nuclear effective charge. You wrote this down yesterday, yes? You probably were like just writing it and weren't really quite understanding it. It's based off the charge of the nucleus. So that's our lab sheet for today. Okay. Explain how the atomic radius trend exists across the period and down. So I'm going to talk about how when you go this way on the period, what happens to the radius when you go this way? It decreases. Okay. So why does it decrease? Because as you go from, let's say, sodium to argon, how many protons does sodium have? Protons. 11 protons. How many protons does argon have? 18. Who has a stronger nucleus? Who has a stronger nucleus that's going to be attracting any electron? Argon. Argon has 18 attractive protons trying to attract all the electrons that exist around it. Sodium's only at 11, right? So if you're super attractive, so the nucleus of argon is more attractive, what does it do to its electrons? It pulls them in. It's attracting them in. It's opposites attract. Positives attract negatives. So if you have more positives inside the nucleus, it pulls in the electron cloud even closer because it's like just an attraction. So this is a small radius where this one's a little larger. So that's called, that decreasing atomic radius to the right is due to ZEFF, so ZEF. ZEF is nuclear effective charge. And that kinda, like, logically makes sense. The effectiveness of the nucleus's charge controls the size of the atom. So if my charge, if my nucleus is really effective in its charge, has a high number of protons, it is really effective and it decreases the size of the overall atom, so it pulls it in. So let's do between aluminum and phosphorus. Aluminum and phosphorus. How many protons does aluminum have?
13.
How many? 13? 13 protons. How many does phosphorus have?
15.
15 protons. Who has a greater effective nuclear charge?
Phosphorus.
Phosphorus. Who has a smaller atom then?
Phosphorus.
Phosphorus, because it's got a higher charge, so it pulls in its electrons. So that's how it exists across a period. And that's just because in sodium's period, what period am I in exactly for sodium? What energy level is that? 1, 2, 3. It's in the third period down. So that's the third energy level. That means all the electrons are in that same, everybody in the third period, sodium, magnesium, aluminum, silicon, blah, 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 blah. They all have electrons in that third outer shell, that third energy level. So they're all the same distance away from the nucleus, except with a stronger nucleus, you pull your outside energy levels in closer. That's why argon happens to have a small atom. But this is different when you go down a period. Down a group. So going down the group, let's go sodium to cesium, okay? Who has the greater atomic radius, the bigger atomic radius?
Cesium.
Why cesium? But there's a reason why. It's not ZEF this time. Yeah. It's the shielding effect, yes. Because how many shells, energy levels, shells are our energy levels, you'll hear that word interchanged. How many around sodium? You just told me. 1, 2, 3 are around sodium because it's in the third period. How many around cesium?
6.
6, 1, is it 6? Yeah. 1, 2, 3, yeah. So I'm not going to draw 5, 6. Okay. So it's just got naturally more shells, so it's naturally bigger because it's got more electrons in it as well. This has nothing to do with the number of protons. It's just like build up, build up, build up, build up. So when you're comparing things across a period, you have to talk about its proton pool. When you're talking about things going down a group, you're just saying, I have more energy levels, therefore I'm bigger. It's like an onion. Who gets that? Who feels like that logic is okay? All right, I got a couple people I got to get on board here. So, but we did talk about the energy electron shielding effect. So the electron shielding effect is the term I use to describe the trend down this group. And this is like more actually related to the ionization energy and those other ones. So if I am comparing the energy it takes for me to take an electron from sodium's valence shell versus cesium's valence shell, who is it going to take? Who's going to require more energy for me to take the electron? Why sodium? All right, so because smaller, first of all, and so the nucleus is very strongly attractive. And that's just simply because it is naturally smaller. Cesium is like, it doesn't even know it has a valence electron. It's so far away. It's like, that's on my child? Yep, guess so. Okay, so that one's going to be really easy to pluck off. So this one's got a low ionization energy. The energy takes to take that electron. This one has a high ionization energy. The energy is to take that electron. And that difference is due to the shielding effect, because there's like a shield between the attraction of the nucleus and this electron. There's like so many electron energy levels in between. That nucleus in the middle barely even knows it has an electron, much less can attract it, because it's just so far away. So that's what the shielding effect is. It's the effect of shields. Let's look at some more. Let's look at some more things you should have learned from the video. Between aluminum and aluminum ion, what is really the difference between those two? The what? Number of electrons. So what happened? Lost 3 electrons. So aluminum, that looks like, let me just keep scrolling around here. Aluminum had 13 protons, 13 electrons. Aluminum ion has 13 protons and 10 electrons. Okay, so let's say this one was this big. How big is this one? Bigger or smaller? Smaller, because it actually lost the entire, let's see, aluminum's got 1, 2, 3. It's got 3 shells. So I'm just going to draw it like this. Okay, there's 2 shells. Why are there only 2 shells? And this one not 3 shells? Right, so those 3 electrons that were here, they were like here. 1, 2, 3. They were in that very outside shell. When you lose it, you lose it. It's gone. The whole shell's gone, so it actually is smaller because you lost 3 electrons. So cations, 3 plus, cations are smaller than their parents they came from. So if I was an anion, give me a good example of an anion. And that's something with a negative charge. An element. Yeah. It actually will never form a -3 charge. That's because how many electrons would aluminum have to move to get over to noble gas electron configuration? 5. That's 5 electrons it would have to gain. That's way too much work. It would rather lose 3 by bouncing back from aluminum to magnesium to sodium back to neon. That's way easier. Never will you see aluminum with a 3- charge. So what would form a 3- charge? Okay, so chlorine would form a -1 charge, right? So chlorine with 1, 2, 3, yeah, 1, 2, 3 shells has how many electrons in its valence shell? You watch this in your video too. Shout it out loud. Just give me something. Not quite. Just straight chlorine, not chloride. Not with a negative charge. Go back one. 7. What group is chlorine in? Do you remember how to count your groups? Oh yeah, that's the name of the group. What number group is that? 7. I'm going to point to that periodic table. That's group 1. How many valence electrons does group 1 have? 1. Group 2 has 2. Group 3 has, group 4 has 4. Group 5, drop it. Oh, no, actually, no, this is right. Sorry, group 5 has 5 valence electrons. Group 6, 6 valence electrons. Group 7, 7 valence electrons. Group 8, 8 valence electrons. It goes in order. There's no way you cannot know the number of valence electrons. So we know chlorine has 1, 2, 3, 4, 5, 6, 7. Those are 7 electrons. When it becomes chloride with a 1- charge, what happened to its electrons? It gained 1, right? Well, it's got to put, there's 7 valence electrons here. It's got to put that last one it gained in this shell because it doesn't have an extra shell. That's where it belongs. But once you add 1 extra electron, that extra negative charge actually repels all these other ones. So what do you think it does to the electrons? Do they scooch together or do they go out? They go out. They repel each other, and as they repel each other, the atom gets bigger. And so that's why chlorine, the parent atom of chlorine, is smaller than the ion form because it has an extra electron. It makes the shell bigger because of the repulsion within it. There's a lot of details here, but I want you to overall know the trends and then 2 reasons why the trends occur. ZEF, nuclear effective charge, and then building of shells or electron shielding. So let's look at some more of these and then we'll kind of conclude where we can on trends. These are questions I need to go over from 2 days ago because we didn't actually finish going over some questions that were relevant for your test. So let me skip down here. Energy levels n equals 1 and equals 2. There's the off-ball diagram, like this. 1, 2, this is n equals 1, n equals 2. This is just saying energy levels build from lower to higher. But these are kind of far apart. Once you get up to energy level 3, 4, 5, 6, what happened to the spacing between those versus these? Okay, so this is closer, then these are farther apart. So that difference makes a difference in the energy loss as well. So if I drop from n equals 3 to 1, that's a big amount of energy. But if I drop from energy level 6 to 4, that's very minimal energy differences. So you just need to know that there are differences in the energy differences between the levels. And that's just a fun fact you got to know. And you can see it on the Bohr model too. It's not like it's not there. Okay, and then yttrium. Can you tell me the electron configuration of yttrium, which is Y? You should have a periodic table someplace for that. Give me long form, okay? Okay, so you're going across the periodic table, 1s2, 2s2, 2p6. Okay, if I stop at 3s2, who am I describing? Magnesium, okay? Okay, 3p6, keep going. 4s2, 3d10, if I stop there, I'll be describing zinc, so you should be pointing at zinc, and then 4p6, and if I stop there, I'm describing strontium, good, and then lastly, 1, 2, oh, I'm sorry, I'm going to vanadium, sorry, that's 41, okay. Now, if I look at this big long line of numbers, what's the highest energy level that the electrons reached? 5. 5 is the valence shell. So if I'm the valence shell, 5s2, that's my shell. That's also my number of valence electrons. So the transition metals, you'll notice I skipped when I was going 1, 2, 3, 4, 5, 6, 7, 8. So if you don't have to know how many valence electrons they have, but if you look at an electron configuration, you can figure it out. So first thing you look for is the highest number. That's the energy level. That's the very outside energy level. And then how many electrons does it contain? 2. So that's the very outside energy level. Those are the loose electrons. Those are the ones that are reactive that you can lose or you can even add to. But if I'm a metal, I'm going to lose those because I always want to lose metal. Metals always lose electrons. So if you scratch those, that means you lost 2 electrons. So what is yttrium's charge? Y what? 2 plus, because it lost 2 electrons. So you can figure that out from the electron configuration. So I can ask you some crazy ones. Just look for the highest number, look how many electrons are there, and that's what it could lose. It actually could lose 1 more, but I'm going to kind of be flexible with you guys there. Okay, how do we feel in periodic trends? Can you describe the 2 features or characteristics of the differences across the group? Across the period and down the group. Okay, that's harder. Okay, let me see if I can help you another way, because I sometimes still am not sure where we are falling. This guy, Bozeman, Mr. Anderson, I'm going to turn the lights down. He describes electron configurations and periodic trends together, because they're like holding hands. They are married. They go together 100%, and that's the electron configurations cause the periodic trends to occur. So I'm going to show you this little diagram, or I'm going to show you from his video. And this is called the all-thought diagram, and it's called the diagonal method. This is how I learned it, but it was simply memorization. I had no idea what the heck I was talking about when I was your age. And I feel like the periodic table going across it like a book makes more sense. But if this makes more sense to you, then you learn it this way. So let's listen to him for a little bit. I want you to take 5 bullet points of notes on these 2 videos I'm going to show you. So just 5 bullet points anywhere so that you're engaged the whole time. You're not falling asleep on me here.
Essentials video 5. This is Hi, it's Paul Anderson, and welcome to Chemistry Essentials video 5. This is on electron configurations. When I took chemistry, I remembered having to do electron configurations. I remember this chart and these different orbitals and this diagram, and I learned how to do it, but I never really knew what I was doing. And so in this video, I'm going to show you how to do electron configurations. We'll do that at the end, but I also really want to tell you what's going on behind the scenes. And so all electron configuration is simply the distribution of electrons, so where the electrons are found in atoms or in ions. And so a good way to figure that out is to look at their ionization energy, which is going to be the amount of energy it takes to pull an electron away. And so we can quantify that by using Coulomb's law.
And we're not going to worry about quantifying, meaning making a number with it. We're just going to say it has a big ionization energy or it's got a little one. So we're making more qualitative observations about that. So what he's saying is electrons are distributed a certain way, and that will determine the ion charge that they achieve. 1 plus, 2 plus, 3 plus, and that's what we were just talking about from the group number, is the valence number. And then if you have a really low ionization energy, you're going to give up those electrons no problem. So you're going to give them away. So you're forming a plus charge or a minus charge?
Plus.
A plus charge, because you're losing negatives. You're losing those electrons. If you're like, heck no, I want my own electrons and I want more, I'm going to take other people's, then you're going to form a negative charge. So it's all going to really come together as soon as we can get that light bulb to go off here.
And so what we can do is we can work our way out from the electrons on the inside to those on the outside. And when we're done, we have a pretty good picture of where all those electrons are. Because in most atoms, they're going to be multi-electron. They have many electrons. What we'll find is they're going to be organized into shells, subshells, and then orbitals. And all of those are going to have similar ionization energy. And there's a chart on ionization energy that's the most important one. Now, if we look at these orbitals and subshells, what we'll find is that the ones on the inside are going to be, or the inner electrons are going to be called core electrons, and the ones on the outside are going to be called valence electrons. And what's interesting is that those on the inside, once they're filled, will actually shield the valence electrons from the power of the nucleus itself.
Okay, we're good so far. Using a lot of terms.
And so let's look at the first and simplest of electrons. We've got hydrogen right here, 1 proton, 1 electron. And so Coulomb's law allows us to quantify the force between the...
And I'm gonna skip the Coulomb's law because that's something we read a little bit about in our worksheet, but that's not the important part of this video.
Made sense. And so where do they come from? It's quantum mechanics and it's quantum numbers that determine that. But if we're looking at...
So what he's saying is that where are all these numbers coming from? These 1, these p's, these letters, these exponents, and he says they come from quantum numbers. So 2 days ago we talked about quantum numbers. The first number was the energy level number. That's 1 through 6 or 7. The second number was actually a letter, right? Quantum numbers, but it was a letter. It was S, P, D, or F. And then we actually can superimpose that here on the periodic table as we did with our blocks. The third number was more of which orbital or how many orbitals are in that sub-level. So like S sub-level, D sub-level, P sub-level, F sub-level. They have different number of little spaces for orbitals. Yeah?
Did you say the first quantum number was?
The principal quantum number. It's the energy level. I feel like you guys are like super intelligent. What are those quantum numbers? You guys have talked about quantum numbers? And then the last one is about spin, but we don't actually list the number.
Periodicity, in other words, if we're looking at the periodic table, these things would be subshells. And so we're going to have a shell, which is going to be the 1, 2, 3, 4, 5. But we're also going to have subshells, which are smaller. And then within each of those, we're going to have orbitals, if that makes sense, if we go in size. And so let's get to the electron configuration. And so what we have here are the sp, the d, and the f. They come from quantum mechanics. What's interesting about the s is it has only 1 orbital in it. The p has 3 orbitals, so you could have 6 electrons. D has 5 orbitals, so you could have 10 electrons, and F is going to have 7 orbitals, so you could have 14 electrons. So if you want to write this out, you could just write on a chart, start with the 1s, and just write all the way down to 7. Then you want to write right to the...
This is what he's going to draw is called the diagonal off-ball method. It's just it's a way to memorize the order that electrons are filled from the nucleus all the way out. Just like we were like, oh, like you guys are just memorizing by accident. 1s2, 2s2, 2p6, 3s2, 3p6. This is going to do the same thing, and if you like this better, then do it for yourself.
Right to that 1s or 2s, you're going to write the 2, and then you're just going to write p's all the way down. And then you go down to the 3, we'll write a 3 over here, and then you're going to write d's all the way down. You could go all the way to 7, but we'll never really need that. Then you go to the 4, you write a 4 over here, and then you write f's all the way down. And so once we have that, we can put diagonal lines in like this, and then we can do the electron configuration for anything. So you wouldn't even need a periodic table.
So this one requires no periodic table, but I like for you to know how to use your tool because you'll always get a periodic table in the test, right? So I like for you to use both. This is the same way. So it fills in order of the diagonals. We fill up 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. It goes exactly in the order of the periodic table, but those numbers, the top numbers, the 2, the 6, the 10, and the 14, and when you go to F, that's what you would have to know if you tried to use this little cheat sheet here.
You can just do this and you can figure out electron configurations. Let's start with hydrogen. What's going to be the electron configuration of hydrogen? You're simply going to start at the top, and so it's the 1s shell or orbital or subshell. And so what we would write it as is 1s1, and that 1 represents the 1 electron that we have inside that orbital. If we go to boron then, how are we going to write boron? Well, you're going to start here, go here, go here. Boron's going to be a 1s2 because we can only put 2 electrons in there. We then go to the 2s, it's going to be 2s2 because we can only put 2 electrons in that. And then we're going to go to the 2p, and we only have 1 electron left, so we're going to put it there. So that'd be boron. What about neon? And again, you can pause the video and always try it out. Neon's going to be this, so it's 1s2, 2s2, 2p, remember, can have 6, and so we're going to write 6 there. Let's go to the next one. What about sodium, which is number 11? We've got 11 electrons. Well, we could write it out like this, 1s2, 2s2, 2p6, and then the next one goes into 3s1, but you can see how long these electron configurations are going to get. And so we can abbreviate that. And so we could just say it's neon, put that in brackets with the 3s1. So that allows us, we just write the noble gas in there, and then we can add what's after the noble gas. And so here's a couple for you to try. Could you try chlorine, which has 17 electrons, or silver, which has 47? I'll put the answers in the video descriptions down below.
So if you do chlorine without looking at the periodic table, you could by saying 1s2, 2s2, that's 4 electrons so far. 2p6, we're up to 10 electrons. 3s2, which is 12 electrons. And then how many go in here? 5, so you start at 3p5. So that's just another way. Who likes that better? Some of us are like, we don't need the periodic table. We do. Okay, cool. Let's look at how this relates to periodic trends then too.
Hi, it's Paul Anderson, and this is Chemistry Essentials Video 6. It's on periodicity. In other words, it's going to be the patterns that we see in the periodic table. Now, what determines that is going to be electron configuration, and we configure that out using the Aufbau principle, which is actually German, and it means the principle of building up. So we're building up from lower to higher energy levels. And so what we can find is these trends that start to emerge, but it's most important, instead of just memorizing them, that you really understand what's going on inside the atom that determines those trends. And so periodicity, remember, is going to be derived from the electron configuration. In other words, where the electrons are. We can determine that by using the Aufbau principle. And if you were to watch the last video on electron configuration, I think that'd help a lot. But what's the meaning behind this? It all comes from Coulomb's law, which helps to explain electron configuration. And also helps to explain these trends. It explains changes in the ionization energy, changes in the atomic and ionic radii, how big the atom or ion is, electronegativity, and finally the ion charge. And so if you really understand Coulomb's law, you can kind of work your way through this on the periodic table. Why is this important? We can use the periodic table to make predictions, especially about things that we haven't even designed yet. And so if we look at the periodic table, this on the right side is going to show us which of these are going to be filled over time. But if you look at the periodic table, we'll find trends. And so here's hydrogen. What we really need to do is take helium and then put it over in this S block. It's going to make us, it's a little easier to understand. And so what we're going to have are energy shells, and then these would be subshells within that. And so one thing you should understand about the periodic table is that this F block should slide right in here.
Did we talk about that? We talked about the F block really, but that's not convenient for a textbook to put on their front cover, so we pulled it out. We humans manipulated this to make it look prettier. It looks like this for real.
It'd be hard to write a convenient periodic table, but that's really how it should be set up. Generally, we've just put it down below. And so what's guiding this or explaining the electron configuration, remember, is Coulomb's law. And so it's pretty simple. If we look at the protons on the inside of the nucleus, they have a positive charge. The electrons have a negative charge. And so Coulomb's law says we just multiply those. In other words, the bigger they are, the bigger the force between the two is going to be. But as we increase the radius, the distance between the nucleus and those electrons, then we're going to see a decrease in that force. The one thing that you have to add to that.
So my mathy people, you like this part because you see that if you have a strong attraction between charge and charge, so protons and electrons, then it's the distance between them that's really limiting the strength of attraction. So if you have a small distance, you're dividing, that says divide by r squared, which is radius squared. So basically you're dividing by a small number, which means you have a large force of attraction because you're dividing by something really small. If you're a math-minded person, that makes sense to you. If you have a large distance between them, that means you're dividing by a large radius, and that large radius, when you divide by a large number, means you get a really small force, and that's what F means, is force of attraction. That's what I was talking about, me versus, between the distance between me and Kendall, large distance, low attraction, because he's going to go, react with somebody else. But me, and when I was standing next to Caroline, then small distance, large force of attraction, she's going to hang out right here, because the nucleus always attracts its own electrons. And that's just called Coulomb's law, and it does have a quantitative number to it, but that's an AP level concept. Okay, and then I think he talks about Coulomb's law the rest of the time. All right, can we look at problem set 6 a little bit to make sure that we have that part taken care of? Because I know that yesterday you guys did a really good job of trying to walk yourself through some of those, but I want to talk about specifically the table at the bottom. Because you will see a table just like this, almost exactly with the labels and everything, on your test. So you notice that the proof one, the next problem is really just like, I took a couple problems of the problem set and changed the letters and numbers, right? So I want you to make sure you're good with this. So let's just do the first one. Before you do that, pull out a periodic table, and I'm actually going to write the letters here so that you can see them. I'll write them in red. All right, so lithium, beryllium, boron, and carbon. So lithium is like over here someplace. Beryllium is right next to it. And then boron is next, and carbon is next. So that's really nice. It's in the same period. It makes life easy. So if you look at your hands, and remember atomic radius is the only one that's the right hand, metallic nature follows that trend. It's almost exactly the same trend. And the word metallic means that you lose electrons. Okay, so all metals lose electrons. So these over here are going to be the most metallic. So if you're going across here, tell me what letter you put for each one. Most metallic. Lithium. Let me tell you why. It's because it's the farthest over, farthest to the left. Lithium is like, heck yeah, I'll lose that one electron I've got, because it gets to backtrack itself to look like the noble gas electron configuration of neon. No, of helium. Okay? So lithium is most likely to lose electrons. The rest of these will lose, maybe. Beryllium, well, these probably will not, because they're more non-metals. Okay? Largest radius. Say it out loud. Lithium again. Okay? They repeat themselves because if it's the farthest to the left, it's going to be the farthest to the left the whole time. Highest ionization energy. Carbon, because it's farthest that way. That means that carbon in particular does not want to lose its electrons because the ionization energy is very high. It's a high amount of energy you have to put forth to take carbon's electrons. Lithium's like, I have electrons, please take mine. Okay, this on this side will always lose electrons. Where are we at? Lowest electronegativity. Lithium, because it's farthest to the left. So you know anything that's, and that's what this arrow says here. The electron, all of these EA, IE, and EN, they increase to the right. So if you're trying to go the lowest, you choose the one on the left. Highest electron affinity. Carbon, again, farthest to the right. All right, let's get down. Which little row should I do right now? I did the first one. You guys tell me. I'll choose more. Yeah, thank you. 1, 2, 3, 4, 5, 6, 7, 8, 9. The last one? All right, that's fine. All right, nickel, platinum, krypton, and iodine. Okay, so where's nickel? Nickel's here in the middle someplace. Where's platinum? Down below nickel. Okay, let me draw this a little better. Nickel is here, platinum is here. Krypton and iodine are next to each other here. Okay, so they're kind of scattered. That one's a harder one. Okay, but your trends still stay true. All right, so the most metallic means farthest this way. What do you guys think? Nickel is farthest left, but so is platinum. They're both the same leftness, so it's the most left and downness. Okay, so platinum. Okay, so that's going to be, and that's because nickel has a smaller radius, platinum has a bigger radius. You have a bigger radius, those electrons out there are not as attracted to the nucleus, so they leave. They are lost. Largest radius. Here. Platinum again. So you're seeing a trend. The most metallic is the one with the largest radius. Highest ionization energy. Krypton, okay? Does krypton want to lose any electrons? No, it is perfect in all ways. It is a cool kid. It is a noble gas. It has how many valence electrons? 8. It is happy as can be. Octet is what that word is, octet. Happy, it doesn't want to lose any. Lowest electronegativity. Lowest electronegativity? Even, yeah, so you're looking at you're saying, oh, they're both to the left, but you want to go left and down. So the one that's got the lowest is actually closest to this corner of your finger right here. So that would be platinum in this case. And then highest electron affinity. Who wants electrons? This one's a tricky one. I'm sure you're thinking, oh, krypton, because krypton's the farthest up and to the right. But did we just talk about this? Krypton is happy. It's a cool kid. It doesn't want any more electrons. So you're backtracking, you go, iodine, because iodine actually needs one electron to look like the electron configuration of a noble gas. That's a tricky one, though. Good job, Natalie. Yeah.
So for on the farthest right, they're good.
Yep, they're happy to do. All right, can I go over anything else right now on problem set 6? You guys talk to me, okay? I haven't heard much from anybody here. Okay? All right, well, pass up problem set 6. Okay, one question. Thank you, Emma. The second, beryllium, magnesium, carbon, and strontium. Yes. Beryllium, magnesium is right below it, calcium, and strontium. That one's nice because it's right down a row. So, most metallic, farthest down into the left, which is strontium. Also the largest radius. That's the two the same. Highest ionization energy, what do you guys say? Highest ionization, so it goes up and to the right. Beryllium. Now tell me why. Don't say, oh, because it's at the high and it increases up and to the no. Tell me why. Why is it so difficult to take beryllium's electron versus strontium? Because it's smaller. That's it. That's it. Smaller radius means mom's got a tight hold on the electron. It's difficult. Take away. Okay. Lowest electronegativity? Strontium. And then highest electron affinity? Beryllium in this case too. In that case, that's how the trend works. Okay. Yes. Gallium, germanium, arsenic, and selenium. They are a little quad, little 4. No, gallium, germanium, arsenic, and selenium. That works exactly the same way as the lithium, beryllium, boron, and carbon because it was across a row. So anything that's the same will let you do, but and down because we just did one exactly like this, one exactly like this, and then we did a scattered one. So I think I've covered the gamut of types of groups I would give you. Okay? All right, so here's what I want to do. I want to do the lab first. We'll see if we have time for the quiz. Okay, so I know, because I can always give you the quiz tomorrow, because if I don't get to you today, I will get to you tomorrow, okay? The lab is very easy, but you need to make sure that you write down your observations as you go, because you'll forget what color things were. So I'm passing back the plain test, and I'll let you guys put the problem set 6s in the box before you leave me if you have one more question you need to ask, okay? I'm trying to be flexible so you can ask me questions, so I wasn't here yesterday. I can put it in the box, but we'll see real fast. Can I explain the lab? All right, let me explain the lab for you, and then I'll let you go. Okay. Listen. Yeah, actually, oh, actually, no. I have some people absent, so just help you guys wait. Let me explain the lab, and I'll get extra papers and whatnot from you. Okay. So this lab is called the flame test lab. We are taking fire, Bunsen burners, and we are exciting electrons. Okay, we've electrocuted them. Now we're torturing them with fire. And that means that you're going to see the electron. Actually, are you going to see the electron jump up or fall down? how are you going to see it fall down? It will emit light, most likely, in a visible spectrum of color that we can see. That's all we can see. We're not like butterflies. We can't see in UV, okay? Did I tell you guys that? Butterflies can see in UV. They're cool. They're way cooler than we are, okay? And plants push out oxygen. They're also way cooler than we are. Okay, that's just how nature works. But we have to get the Bunsen burners prepped. Do you remember how to set that up? It's in the lab notebook if you don't. Okay. You must stay in your try area. So I put all the same solutions between these two tables that are between these two tables that are between these two tables. So you're going to kind of test all the solutions at your table and then just say, all right, lab group behind me, you ready? And just switch with them to make sure you see all the things that you need to see. I'm going to demo how to do that. And then these are called the nodes. So I'm telling you, calcium, blah, 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 and you're going to see the colors. You're going to write calcium, and you're going to tell me the color. You're going to write sodium, you're going to tell me the color, and so forth. And we should have time, so I'm going to give you unknowns. And the unknowns, you identify the substance based off the color you see. Does that make sense? Because you'll have a full list of what the ions are and the colors they make. And then I'm going to give you unknowns, and you're going to be like, oh, it made purple, so it must be ponies, or whatever it is, okay? So you will need glasses, or safety glasses. You will need to set up the Bunsen burners, and then I'm going to demo. So I want to demo this in about 3 minutes. So go get same lab groups, go. Yes, go.
So I didn't know that problem set